So let's now discuss the field of optimal control. So optimal control is actually another way of designing a state feedback controller. So let's think about what we know about these systems already. So we know in an open loop system we have the equations x dot equals ax plus bu, y equals cx plus du, and the stability of the system is determined by the eigenvalues of matrix A, which relate to the poles of the system, and what we don't want are positive real parts to the eigenvalues, otherwise the system will be unstable. When we use full state feedback control, then we set u as minus kx, and we can substitute that then into these equations in order to get the slightly modified form what we get for state feedback control, such that x dot equals a minus bk times x and y equals c minus dk times x. And now the stability of the closed loop or the state feedback control system is now determined by the eigenvalues of the matrix A minus BK. So we can look at that now as a state feedback system using signal flow graphs, which are quite a nice way to depict what's actually happening in terms of what's happening with the signals. We've already looked at this a bit in the past, so I shan't go through it in too much detail, but basically the bits in black correspond to the state space model. And what we've got all the A and the B and the C matrices. The important thing is we're calculating intermediately the X, the full state of the system, and we can tap this off, multiply it by the minus K vector, and use it as the input to the system. And of course there's also a reference input as well. Now, when we're designing these systems using pole placement, what we decide to do is we say, well, let's try to get a value of k to get poles or eigenvalues where we want them to be, which is fine and it works well. But it's not immediately obvious where the pole should be in the first place. So obviously we know that they've got to be, they've got to have negative real parts, otherwise the system will be unstable. We know if they've got imaginary components, there's going to be some oscillation in the way the controller operates. So there are certain things that we can say about it. And we can also say, the bigger the magnitude of the pole or the eigenvector is, the faster it's going to try to get to where we want to go. But we haven't, it's still a little bit of an arbitrary decision to make in terms of, where these things should be. So people have been discussing this for a long time, and there are now more principal ways of choosing the value k than just deciding that this is the pole value that you need. And that's the idea of optimal control. And the idea of optimal control is that we're going to define a criteria for optimality in terms of a performance criterion. And basically to do this we have to define a cost function, and we want to minimize this. And we want our controller to basically come up with a minimum cost as defined by our cost function. Let's think about a cost function that could be valuable for driving a car. Imagine you're driving a car, you've got to go from Plymouth to, Scotland, which could be a long way. Now, one of the things you could minimise is the time taken to go to A to B, right? So you could say that I'm going to just add up the time it takes, I'm going to equally weight it across the entire journey, and the longer I take, the bigger the cost. You could do that, right? So you want to get there as fast as possible. You could also say you're going to minimise the amount of fuel you're going to need. That would be another way of doing it. So you say, you're not so bothered about how long it's going to take, but you want to get there with the minimum amount of fuel possible. So you look at the fuel flow at any point in time, and you add up all the times across you add up all the fuel flows, integrate it across the entire journey, and come up with the total amount of fuel used, and you want to minimise that. It could also be that you want to minimise the overall financial cost of the journey, which would probably also relate to your time and also the cost of the fuel, in which case you'd be adding up cost per hour over the entire journey. Now, often we'll be using actually a quadratic measure of deviation from from what we think that the system's doing. One reason for doing that is it makes the analysis a lot easier. Another nice thing about using a quadratic measure is if we have a linear error basically, and say, look, we've got this bit was good, this bit was bad, so you had a negative value here and a positive value there. If you're not careful, the negative and the positive can cancel out. If you have a quadratic measure, then an absolute deviation from something is always going to come into the equation. But basically, it makes it mathematically tractable. That's one of the reasons these things are done. So here is a typical cost function for an optimal control problem that we'll certainly come across quite a lot. So the cost is now the integral from 0 to infinity of what effectively the x. There's a factor for x and there's a factor for u. So the factor for x is going to be the quadratic deviation of the state from 0 multiplied by a weighting factor q. And the u term, the u transpose ru, that's going to be a weighted function, which is a quadratic weighting on the actual control you're using. So let's just go through that a bit more detailed. So x transpose times this weighting matrix times x is a quadratic term relating to what the value of the state is. It's trying to say, if the state is anything other than 0, then there's going to be a cost added in, and q is typically just a scaling factor. And if we want this to relate to the output of the system, we can put q in as being basically the output vector, if you like, multiplied by itself. So it's the weighted distance of the state from its origin. That's basically what it's saying. So really what it's saying is, again, another way of putting it is, if I want the system to follow a certain reference, it's penalising it a lot if it's not getting to that reference. And this is going to mean it's going to, if this is a very strong term, it will try to follow what it's actually been given to do. It's trying to very much get to the goal that you're giving the system, meaning it will get there quickly and it should deal with the settling time effectively as well. So it does a good job tracking. On the other hand, the term U transpose RU relates to the input control into the plant that you're giving it. So this is going to be basically big if there's a huge control going into the system. So in terms of the car, the first X transpose QX will penalise you not being at the destination, whereas the U transpose RU will penalise you using a lot of fuel or using a lot of control on the car. So it's the weighted square control activity. And it penalises you using aggressive control inputs, right? So this would penalise you pushing the accelerator and using petrol or whatever. So this is going to try to minimise the amount of power or amount of energy you're using in your control, and at the expense, it doesn't care about how good you're actually doing the task that you're trying to do. It doesn't care about the tracking performance. So if you've got these two terms, there's obviously going to be some kind of compromise, and the optimal solution will be basically the solution which finds the overall minimum value of J. So it's going to be a trade-off between how good you are at minimising state deviation from 0 in this case, and control deviation from 0. So from the expression of cost then, we want to give now our controller system a value of K, the gain of the system, which minimises this cost. And that's the idea of using this minimum, using this optimal control strategy. We're saying now we want to design K, but we want to do it on the basis of minimising this cost function. So this is what that is saying. It wants to find the K that minimises this cost function. Given that we've got a feedback controller system, a state feedback controller system, which is based on this state space model. Now, the solution to this is outside the realms of possibility within this particular module because it's a bit trickier. But basically, it's found by using dynamic programming methods. You'll come across them if you do machine learning. And you can basically write down the equations. There's obviously quadratics in there or else. So it's an optimization of a quadratic problem, and it comes up with an optimal solution in terms of the expression from the gain. And the solution for the gain ends up being along the line, well, if this is the solution for the gain, k is going to be equal to r to the minus 1. So inverse of r times the transpose of b times p, where r is an invertible function, p is a symmetric function, and satisfies what we'll just see in a second is called the algebraic Riccati equation, which is the following: a transpose p plus pa minus pb inverse of r times b transpose p plus q equals 0. Right? So it's actually quite involved, but absolutely trivial to implement in Matlab. When you're doing it by hand, it's a bit trickier, and we're going to go through one by hand because it's kind of a question that could come up. And if you do get it, you're not going to get complicated systems to analyse. So let's consider now applying optimal control as an example to the control of a mass position. And we're going to consider a 1 kilogram mass, because then m equals 1, and we can forget about the value. So let's write down the equations of motion for this system. So we've got a control u of t pushing this mass m of mass 1, and it's resulting in a displacement y of t. So force equals mass times acceleration. So u, which is the force, equals the second derivative of the position. So d squared y dt squared multiplied by 1, because 1 is the mass. We want to write this down as a state space model. So we want to get rid of the second order equation, and we want 2 first order ones. So we have to choose states. So first of all, we're going to choose a state y, and we'll also choose a state dy dt. So it's a bit more obvious starting from the dy dt, since we have to write down a state which is smaller than the second order expression we have. So we want 1 order less than d squared y dt squared, which is going to be dy dt. And because we've got to get back to the first order, we've got to get back to the displacement, we also obviously need the x1 equals y as well. So first thing we do is we write down the first state equation, state space equation, which is going to be the fact that we can see immediately that x2 is going to be x1 dot. And the second one's quite simple, because we just substitute in our x2 in the first expression we had for u equals d squared y dt squared. So x2 dot equals u. Right. So now we've got our very simple state space model. x1 dot x2 dot, written as a vector, equals this A matrix multiplied by the state plus this B matrix multiplied by u, right? And the output's going to be x1, so we care about the output being y, which is going to be the displacement. So we've got the A matrix, the B matrix, and the C matrix. So we're going to use a controller which basically operates by minimizing the distance, which is going to be y squared, and it's going to be some scaled version of the control, so rho times u squared. So in this particular case, obviously we're talking about 1-by-1 values for y and for u, so we don't have to write these in matrix form. They can be put in directly as scalars. We're going to formulate this as the optimal control, linear quadratic regulator problem. That's what it is. The Q matrix is going to be, in this case, it's going to be the output equation vector transpose multiplied by itself. So that's going to be basically 0, 1 multiplied by 1, 0, and it ends up with a 2-by-2. The R term is actually going to be the, it's obviously this, it would be a matrix if we were doing it in a matrix high dimensional system, but since we just, well, it's basically a 1-by-1 matrix, and that's rho, that's the penalizing factor on the control. So the inverse of that, of a 1-by-1 matrix is 1 divided by the value, so R to the minus 1 equals 1 divided by rho. Now we've got to solve the algebraic Riccati equation, because we need to find out what P is, and after we've got P, then we can find out what K is. So we've got this equation. What we have to do is we have to stick in all the values that we've got and then solve for P, right? So we've got to go through this equation and stick all the things in we know. And P is going to be a symmetrical matrix. So basically it means that we have a top value of P1. The next we have the P2 at the top and on the bottom are the same value, and the third value is going to be a P3. So we substitute all the values that we know into the Riccati equation, right? So in goes the A, which we then transpose, in goes the P, here's the P, here's the A, take away P, B, R to the minus 1, B transpose P plus Q equals 0. And then we have to just go through terms by terms, evaluating it until we end up with something which is going to be just a single matrix, and then we're going to solve the single matrix. So the way I always do it is just do it in pairs. So first of all, do this thing, transpose this, so the row goes to the column, so that goes to that, that goes to that, multiply this out, right, 0 times that times 0 times 0, boom, 0 times 0, 0, 0, one lot of P1 and one lot of P2, that's that done. Same for the second component here, we just go through that and multiply it out. Then I'm just basically putting them together and then multiplying them out again pairwise, so multiplying out the first and the second, and then the fourth and the fifth, and then finally just go through and multiply out all the last bits until we end up with the equation which is going to be equal to 0 when after we've put all the terms together. Then you've got to go through and solve for P1, P2 and P3, and you've got basically simultaneous equations for do this. We know this term here is going to be equal to 0, you know this term here is going to be equal to 0, and you know this term here is going to be equal to 0, and this one should be the same. So you have to go through that and solve the equations, which is a bit tedious, but if you were to do this in an exam, basically, you know, you'll get most of the marks just writing down the thing to solve. You don't, you know, solving the equations is a bit of a pain, but obviously, you know, it's nice to have the right results. P is positive definite, so we only want positive solutions. And we'll end that basically means you get positive solutions when we've got square roots. We only want the positive one. We end up with a P matrix that looks like this. So now we've got the P, we know what the R is, we know what the B is, we can actually calculate what the gain is. So 1 over rho 0, 1 multiplied by the P value we had, we end up with an expression for K. And if we stick in rho equals 1, we see that the value is 1 and the square root of 2. So all of that very complicated, or apparently complicated calculation ends up with a very simple solution that just tells us what the gain is in order to achieve the optimal criteria that we actually demanded in the first place. Now, you wouldn't normally do it all by hand if you were doing something like of this nature, and you know, you're only going to get that because it's just a way of making sure you've understood the principles, and that's why that kind of thing comes up in exams. There's also a Matlab function for it, as you probably imagine there would be, LQR, Linear Quadratic Regulator Design for State Space Systems. You can have a look at that in your leisure, and it'll tell you exactly what it's doing. Obviously, that's not going to come up in any exams, but it's, you know, if you want to build these things in the real world, just like you wouldn't normally, you know, if you're dealing with a big system, you wouldn't do pole placement by hand because you'd be having to muck about with these huge matrices. Anything more than 2 by 2 is a nightmare. So normally you would use a Matlab function to do these things. So that's very simple to do in Matlab. We put the A in, the B, the C in. We tell it what the R is. We tell it what the Q is. We just call linear quadratic regulator with A, B, Q and R, and out pops the same value as we had before, which is always a nice thing to see.